Hello everyone, welcome back to my channel. My name is Sakshi and today we are going to solve a modification of the problem subsets which we solved in the previous video. If you haven't looked at my previous video on subsets, go have a look at it. You can find the link in the description below. Today we are going to solve the problem number 90 on LeetCode, which is given an integer array nums that may contain duplicates, return all possible subsets. That is the power set, and the solution set must not contain duplicate subsets, and we can return the solution in any order. The modification here is that the array may contain duplicate elements. Earlier we had unique elements in the array. We will follow these three simple steps to solve this problem. Firstly, we'll look at the recursion tree. After that, we will implement the algorithm, and then we'll discuss the time and space complexity of our algorithm. Now, to understand the recursion tree, let's first look at the case when all the elements are unique. This, from the previous video, we know that all the leaf nodes here contain the subsets that we require. Now let's look at the case when we have duplicate elements. If we follow the previous approach to draw the recursion tree, we get a tree something like this. For index 0, not including 1, we get an empty subset. Including 1, we get this subset. Now for index 1, not including 2, we get an empty subset. Including 2, we get 2. Here also, not including 2, we get 1. Including 2, we get 1, 2. Now for index 2, not including 2, we get an empty subset and we get 2 here. We get 2, 2, 2, 1, 1, 2, 1, 2 and 1, 2, 2. Since there are duplicate elements in the array, we are getting duplicate subsets here. But we do not want to include the duplicate ones. Then how do we avoid them? Think of it in this way, that the left branch means that the element is not there in any of the nodes of the subtree. So you can see that 1 is not there in the left subtree in any node. And similarly, the right branch means that there is at least one occurrence of the element in all the nodes. So there's at least 1 in all the nodes of the right subtree. If we apply this logic to other subtrees of the tree, that means this subtree should not contain any 2, and this should contain at least 1, 2. Similarly, this should not contain any 2, and this should contain at least 1, 2. So this is satisfying the condition that we want it to, but these two trees are not satisfying that condition. So if we remove these two subtrees, what do we get? We get an empty subset 2, 2, 2, 1, 1, 2 and 1, 2, 2, which are the subsets that we want in our answer. That means if we are including the element, then we are following the same logic that we applied in the previous problem. And if we are not including that element, then we should not include any occurrence of that element. So this is the final recursion tree for this problem. Now let's jump to part 2, which is the implementation of this algorithm. I'm writing a recursive function, naming it triggers. Now look at the inputs which I'm providing to this function. Nums, which is the given array, n, size of the given array, index is the current index, a temporary vector which I'll be using to store the elements, and after that I'll be pushing the temporary vector to the final output vector, which I'm taking as RET. Now look at the recursion tree. If we include that element, then we are not changing anything. We will just push that element and we will recurse for index plus 1, right? We are including that element. That means we are pushing it to temp, recurse for index plus 1, and then Now, if we are not including that element, then we have to remove all the occurrences of that element. For that, run this while loop and check for nums of index equal to nums of index plus 1. Here we are assuming that we have the array in sorted order because we want all the occurrences of the element at one place. We'll do index plus plus. Now recurse for index plus 1 and return. In this way, we have avoided every occurrence of a particular element in the subset. Now, when do we push temp into the RET vector? Here also, like the previous problem, we have all the subsets at the leaf nodes. So we reach the leaf node when index is equal to n. We push temp vector into the RET vector and return. Now to call this function, get the size of the array. Now, as I already mentioned, that we have to sort this array to get all the occurrences of one element at one place. I am defining a vector temp, another vector of vectors, which is the output vector, RET. I'll call the function recurse starting from index equal to 0, temp and RET. Now I'll return RET. Let's check. It's working fine. Now let's submit it. Correct. We are good to go. Now let's talk about the space complexity of this algorithm. We have used an extra temporary vector for storing the elements of the array. And the maximum size of this temporary vector can be n when we are storing all the elements of the array as a subset. So the space complexity of this algorithm is order n. Again, we are not including the space taken by RET because that is the output vector. Let's discuss the time complexity of this algorithm now, which is the number of recursive calls into the time complexity of one call. What are the number of recursive calls? If all the elements are distinct, then the number of recursive calls are 2 to the power n, as explained in my previous video. Here, we will consider the worst case scenario will be when all the elements are distinct, and in that case, the number of recursive calls are 2 to the power n. So we will consider the number of calls to be 2 to the power n. And what is the time complexity of one call? This if condition, we have the time complexity of order n because there can be maximum n elements in temp. This is order 1. This is order 1. This is also order n in the worst case. So the total time complexity of one recursive call is order n, and the number of recursive calls are 2 to the power n. So the total time complexity of recurse function is n into 2 to the power n. And if we talk about subsets with do function, we have n log n and n into 2 to the power n. So the total time complexity of the main function is also n into 2 to the power n. So this is the complete solution of this problem along with the time complexity and space complexity. If you like this video, please like, share and subscribe. And if you have any comments or doubts, please leave them in the comment section below. That's it for today. See you in the next video. Bye-bye.